Okay, we're going to start looking at another force today. This one is in many ways similar to what we've done looking at gravity, but there are some differences. So let's get started with that. You will need some paper and you will need calculators today to do some calculations. Okay, we're going to start with a short demo here. What I've got here is just a piece of cotton. And what I'm going to do is I've got a balloon, and I'm going to put this balloon that I've rubbed against my hair onto it, and you should notice that it picked up this piece of cotton. Okay? And did so fairly easily. So what do we call this force? Well, what you probably came up with is it's probably some sort of static electricity, and so we would call it then an electrostatic force, and you'd be right about that. That's exactly what it is. It's an electrostatic force. So when we talk about electrostatic forces, we're dealing with charges. And so that's what we're going to look at today. Electrostatic force. Okay, so one thing that they found as scientists started looking at electricity, and this goes back to about the time of Ben Franklin, and he was actually one of the big scientists in the field, was what causes this static electricity. And what they found was that it's charges that do that. Specifically, it's electrons. Okay? So if we go back to a simple model of the atom, what we'll see is we've got some number of positive charges in the center of an atom, and then around the outside of the atom we've got some electrons. Okay, if it's hydrogen, our simplest atom, there's just one proton and one electron. If it's helium, then we've got two protons, two electrons. And as we continue up the periodic table, we keep adding protons and electrons. And each proton and each electron have a specific amount of charge. And as it turns out, that specific amount of charge is 1.602 times 10 to the negative 19th coulombs. The unit for charge is a coulomb. Both the proton and the electron have the same size of the charge. It's just for a proton, it's positive, and we'll use E plus as the symbol for a proton. We have a positive charge here. For an electron, and we're going to use E minus for that, our charge would be negative 1.602 times 10 to the negative 19th coulombs. Okay? And the charge on a proton and the charge on an electron are our smallest type of charges, and anytime we have charges, it will be some multiple of one of these. So we're going to use Q for our charge on an object. Q is just N times E, where N is just some integer, 1, 2, 3, or so forth. And we can keep going up like that. We cannot have some value that is not some multiple of this charge. In other words, I could never have a charge that is 2 times 10 to the negative 19th coulombs. 2 is not a multiple of 1.602 times 10 to the negative 19th coulombs. Unless it's some multiple of that, I cannot have a charge there, or that size. So we have these things called charges. And between the charges, we get a force. Now, if we have like charges, in other words, both positive or both negative, like charges repel. Opposite charges attract. But now we need to look at and see, well, how big is our force between them? And the equation for the force between two charges is given by F equals K Q1 Q2 over our distance squared. So I want you to take a look at that equation for a moment. Does it look familiar to you? Does it look similar to another equation we've had? Well, what I'm hoping that you noticed was that in many ways it looks similar to our equation for gravity. Our equation for gravity was F equals minus G m1 m2 over d squared. Now, many times we'll leave off the negative sign here, and we'll just note that gravity is always attractive, an attractive force, and that anytime we get a negative number here, or put our negative in, that's all that negative sign means, is they attract. With our electrostatic force, this negative becomes more important, and we need to be a little bit more careful about how we designate things. Because if both of these charges are the same, we'll get a positive value for the force, and that means that it repels. If they're opposite signs, one's positive, one's negative, then we'll get a negative sign for the force, and that means it's an attractive force. So the equations look very similar. The differences are that we've got charges instead of mass, and we also have a different constant out front. Our gravitational constant we gave as 6.67 times 10 to the negative 11th Newton meter squared per coulomb squared. Now with our electrostatic force, our value of K is going to be 9.0 times 10 to the 9th Newton meter squared per coulomb squared. Again, the units, that should be kilograms squared. The units look very similar, except for here we've got kilograms. Here we have coulombs. But do you notice anything about the size of the numbers for these two things? What I'm hoping you noticed is the size of the force is much, much different. Notice how weak capital G is. 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. K is 9.0 times 10 to the 9th. This is a factor of 10 to the 20th difference. If I was to write that out, our electrostatic force is this much times bigger than our gravitational force. Okay, so our force, our electrostatic force, is a really strong force. Our gravitational force is pretty weak. Okay, and in fact, if we were to put together the different types of forces that we know about, we've got 4 forces here. Our first one is gravity. Our second force, which we've talked about right now, is actually an electromagnetic force. We're just going to talk about the electric portion of this